Welcome guys. Now we'll be solving the problem which implements Dijkstra's algorithm. The name of the problem is path with minimum effort. So what does this problem state? You're a hiker preparing for an upcoming hike. You are given heights, which is a 2D array of size rows and columns, where heights of row and column represent the height of the cell at row and column. You are situated at the top left 0, 0. So we are situated at the 0, 0th index, and we want to travel to the bottom right, that is the row minus 1 and column minus 1th index. We can move in 4 directions: up, down, left, right, and we want to find a path or route that requires the minimum effort. So what is effort? Effort is the maximum absolute difference in heights between two consecutive cells in the route. So let's say this cell has 1 and this is 2, so the absolute difference is 2. And likewise for all the path, we'll need to, the effort of the path is the absolute maximum of the absolute difference. So for this path 1, 2, 5, 3 and 5, the absolute difference is 2, and for 1, 2, 8, 3 and 5, the absolute difference is 5, because absolute difference is 6 actually, because 8 minus 2 is 6. So for this example, we need to return the minimum effort to travel from the top left to bottom right. So for this example, the minimum effort is through this path, to the highlighted path, and that is 2, because we can see for all the elements, the absolute difference, the maximum of the absolute difference is 2. So how do we solve this problem? We will start by first initializing the heights, the rows and columns of heights. So m is the row, so the number of rows is stored in m and number of columns is stored in n. And now, so to implement Dijkstra's algorithm, we'll need a priority queue which implements minimum heap. So what does a priority queue store? We store the node and the minimum effort. So how do we store the node? We will store it using the indices I, j. So we need 3 values, I, j and the effort. So we can use a pair of int. And since we'll be implementing the minimum heap, we'll need to change our priority queue likewise. Let's see if the curly braces are in order. And this is how we implement the priority queue using minimum heap. And then we'll need a distance array. As the normal Dijkstra's algorithm, we'll need an array, but since we use the since we are dealing with matrices or 2D arrays, we'll need a 2D distance array. This basically stores the effort, so we'll initialize it. We'll first initialize it to the maximum possible value. The maximum value is 189, and we know we'll start from the source. The source is the 0, 0th index. So we know the distance or the effort from the 0th index to itself is 0. So we'll put the initial value in the distance, and we'll also push the source in the priority queue. So the effort is 0 and the source, the row of the source is 0, column is 0. And now we would need to compute the Dijkstra's algorithm. We'll do so till the priority queue becomes empty, and then we'll first take the minimum value from the priority queue. The minimum value and the distance of the minimum value, or the effort for the minimum value, is stored in the first part of the priority queue. So we store the value in the pair of int. So this first value can be accessed using this, and the second value can be accessed as follows. Which is the index for the row is in the second part of the pair, and the first part of the inner pair. And likewise for the j, it is the second part of the second part of the pair. And that is how we take the elements from the top of the priority queue, and we will need to pop the priority queue as well. So we'll pop the priority queue, and then if our indices, that is I and j, equal the the bottom right cell, that is if we have traveled to the bottom right cell, then we have obviously reached the bottom right cell with the minimum effort. Because we are using Dijkstra's algorithm, we will greedily pick the minimum the node with the minimum effort. So we can with surety say that we have reached, if we have reached the bottom right cell, then we can return the distance, or we can say this as the difference. We can return the difference. If not, then we need to go to the adjacence of this I, j cell. So what is the adjacent of this I, j cell? We need to go in 4 directions as stated here: up, down, left and right. So how can we go to this 4 directions? I'll use this technique where we'll store the coordinates here in a vector pair of int. So we can go we can stay in the same row and move to the next column, or we can stay in the same column but move to the next row, or we can stay in the same row and move to the previous column, or we can move to the previous column, previous row, and stay in the same column. So this is how we move to the four directions, and by iterating through this directions vector of pair of int, we'll get those values. So our new index or coordinates are the new index and coordinates are these. And now we'll check if this row and column index is valid. This condition basically checks whether the row and column index correspond to a value inside the matrix and do not go out of bounds. So if they are inside the matrix, we'll calculate the current effort. The current effort is the max of the absolute difference between the current node and the adjacent node. if the current effort is less than the one that we have already stored. If they are less than the one that we already stored, then we can relax them and we can store the new minimum effort. And since we have now gotten new minimum effort, we can now push this back into the priority queue. And this is the effort. This is the indices, and now this algorithm will continue till the priority queue becomes empty. But in this problem specifically, we will definitely get the answer before the priority queue becomes empty, because we are greedily picking the minimum element. Because the dijkstra picks the minimum element, so we are greedily picking the minimum value. So therefore the control will never reach to this bottom, so we can just return the normal for the sake of returning, we'll return 0. And so this is all the code that is required to solve this problem, and let's run and hope that we don't find any errors. And we have found one error. So it's basically in defining. Yep, it runs fine, so we'll submit. And it submitted successfully, and that is how we find the minimum path effort and solve this problem. So I hope you understood this code. Thank you for watching, and we'll see you in the next video.